Cool, thank you, and thanks for the invitation. It's great to be here. So today I'd like to tell you about a problem called matrix balancing. It's a problem that likely a few of you have heard about, but I promise almost all of you have used whether you know it or not. So every time you compute eigenvalues, whether it's in Python or MATLAB or Julia or R, any other software package, every time you type EIG, behind the scenes by default, these software packages precondition your matrix using this thing called matrix balancing. And only then do they compute eigenvalues on that preconditioned matrix. And for more than 60 years, all of these software packages have used the same algorithm, something called Osborne's algorithm. I'll tell you about it later, but it's somehow a very simple algorithm to state, and yet it's been a long-standing challenge to understand why it works efficiently. So this is a problem I've been very interested in the last 5 years. Today I'll tell you about some early results with Pablo Perillo at MIT, and some very, very recent work with Xufeng and Jelena Diakonikolas at Madison, in which we finally proved that Osborne's algorithm, as it's actually used, converges in near linear time, so really the fastest possible. OK, so that's what I'd like to get to by the end of the talk, at the second half, at least state the result and give you a bit of a sense of what's behind there. The first half of the talk, I'd like to actually stay sort of at a higher level, more conceptual, about how this is related to optimal transfer, which of course is the theme of this workshop. So the sort of point here is that there's a unifying story with four main characters, matrix balancing being one of them, optimal transport being another, other problems as well, matrix scaling and min-mean cycle, often studied separately. And the sort of unifying story I'd like to tell you about is a different perspective which unifies both the problem formulations. Probably the left-hand side is more familiar to optimal transport community. Maybe the right-hand side is a little bit less familiar. But these problem formulations as well as algorithms, and it also unifies analyses. So that's what we'll try to describe in the first half. It'll be a bit higher level and just trying to emphasize the connections rather than the details. All right, so let's get started. OK, so make this bigger. Better. OK, so let's start with the first row. I'll introduce these two main characters, optimal transfer and min-mean cycle. Let's start with optimal transfer. It's probably the most familiar to everyone here. OK, and to introduce this first row, I'll describe things in the language of graphs to make the connections clear, and we'll move to the language of probability very soon. OK, so optimal transfer needs very little introduction to this audience. But in terms of graphs, I'll just say a couple words. You have a bipartite graph, supplies on the left, demands on the right. You have a cost Cij of moving a unit of mass from I on the left to j on the right. And the whole question is, how can you ship supplies to demands in the most cost-efficient way? So you try to find a flow which tells you, for every I and j, how much mass do you move? You want to actually ship all of the supplies from every mu I, ship the right amount of demands to every nu j, minimize the total cost. All right. So as we've seen in this workshop in previous talks, and this has many applications, not just Monge's original idea of moving dirt from ditches to piles, but also from 1700s to 1900s, textbook OR applications like shipping widgets from factories to stores. And of course, the real reason that optimal transport has become so prominent in modern data science applications is that it lets you morph any type of complex data distribution to any other, whether it's not just standard widgets, but could be point clouds, images, shapes, et cetera. OK, so this is stuff we're probably most familiar with. Let me tell you about a different problem. Now, min-mean cycle. This will be sort of the second main character. So the problem setting here is we have so no longer bipartite, just weighted directed graph. So you can imagine edges directed. They all have some weights. And the question is, can you find a cycle, which means a path of directed edges that ends up at the same place? Can you find a cycle for which the average cost is minimal? So I sum up my costs along each edge. I average, and that's what I want to minimize. OK, this has lots of applications for those who like finance. This comes up in arbitrage, and I'll explain that in just a second. But if you like machine learning or reinforcement learning, you recognize this probably as the optimal policy in a simple case deterministic MDPs. If you like TCS or graph algorithms, then you recognize this as the bottleneck of network simplex, et cetera, et cetera. It's sort of an interesting question in its own right. For those of you who haven't seen this before, let me just introduce one application so you can see why you might care about something like this. So we'll talk about arbitrage. OK, so the idea here, I'll describe sort of a slightly different thing. It won't be this exact cost, and then I'll transform it to get this problem in a second. OK, so imagine you want to make money, like many of us might want to do. And we have many different currencies in the world. So I have a vertex for every currency, dollars, Great British pounds, euros, you could have more. I can, of course, go to the bank and exchange dollars for pounds or pounds to euros or things like that. And if I exchange through a cycle, then it would end up with the same currency. And if I start with $1 and end up with more than $1, I've made money. It's what's called an arbitrage opportunity. So let me put totally fake numbers here. So imagine I have a weight of 0.9, a weight of 0.8, and a weight of 1.5. I'll call these W of V's just to emphasize these are not the costs that I'll have in a second. We'll have to do some transformation. But imagine what these numbers let you do is if I go to the bank, I could transfer $1 US to 0.9 euros, and so on. And you could fill in the data for the rest. But even just from this, you could see that actually because 0.9 times 0.8 times 1.5, this is some number, I think it's 1.08 or something, it's bigger than 1. If I go through this cycle, if I go to the bank and stay there 3 times, I'll eventually make money, and I can repeat this. Okay. Obviously, a simplified setting. If this were true, probably markets would not be so efficient.
So that on each edge you have the same price, 0.9 in both directions?
No, there'd be more things, of course.
Then you 0.9, but 0.8, you go in the other direction.
Oh, sorry, that's just...
okay, that's the reason I ask you.
Thank you. Your eyes are sharper than mine. Okay,
I'm paying attention. Okay.
Thank you. Okay, so let's reverse these edges. I'm going to just write this as this is.
Okay.
Okay. Thank you.
Now it's clear.
Perfect. Okay, so let's try to abstract what's going on here and connect this to min-mean cycle. What we want here is a product of edges being larger than 1. So what's going on here is there exists a way to make money. If and only if there exists a cycle such that when you multiply all the edges in the cycle, you end up with more than 1. That's what we just did. OK, that problem looks a little bit different. We'll do some very simple transformations. So first of all, I can renormalize this by taking the geometric mean. If this number is bigger than 1, then if I take a power, it's bigger than 1. OK, now we have products instead of sums. There's a way to transform that. Let's take a log, and let's do a negative log. So instead of maximizing money, we're trying to minimize the cycle. So I'll just take a negative log. And we say that this is equivalent to this average being less than 0. So if I now define my cost C of V to be negative log of W of V, then this is equivalent to having the min-mean cycle be less than 0. For those costs. OK, so just to give at least one concrete example of why people care about this in its own right. All right, in any case, those are the first 2 characters in the story, sort of the first row optimal transfer min-mean cycle. So far, they look a little bit different. One's optimizing flows, one's optimizing cycles. The connection is most syntactically apparent when we take the LP formulations. So that's what we'll do next. The first one is probably quite familiar to this audience. It's the Kantorovich LP. So here we're optimizing over, actually there's really no difference between how I wrote this and the previous one. I could have had mange and kind derivatives, then it'd be a real LP relaxation. This is just a notation change. We're optimizing over matrices P, whose entries just tell you how much mass is shipped from I to J. These are non-negative, because we can't send negative mass. So I have this notation, delta n by n is just non-negative matrices, should the sum is equal to 1. I guess this normalization constraint is sort of implicit here, but I've written it because it'll actually be meaningful the second one, so I can make these more parallel. OK, so we're optimizing matrices here whose row sums and column sums are constrained. So every row ith row sum is mu I, every jth column sum is nu j. OK, and this is, C is just a matrix n by n whose entries are Cij, so this is exactly the same linear cost. Great, we're familiar with this. This might be a little bit less familiar, so I'll describe this in a bit more detail. The idea here will be very similar. So if you believe for me for a second that this is the LP relaxation, then I can draw a similar picture. We're optimizing over n by n non-negative matrices sum to 1. They also have marginal constraints. So P1 is the row sums, P transpose 1 is column sums. But it's slightly different. Here they're fixed. The row sum had to, I was given mu I. The row sum had to be that. Column sum had to be that. Here the row sums and column sums can be anything we want, but they just have to match. So the ith and ith have to be equal to each other. So if I take, for example, the first row sum, this can be any sort of number as long as it's equal to the first column sum. OK, and that's what I mean when I say fixed marginals versus symmetric marginals. So for those who are doing quantum stuff, you've seen these types of symmetric things come up in DFT and things like that.
That's not quantum. Sorry.
In some DFT relaxations, maybe we can talk. OK, in any case, I'm not going to say anything more about quantum in this talk. All right. So the main point for us is just these LP relaxations are not going to be sort of similar, on similar footing. I'll just give you a quick sense of why this is the LP relaxation, although the derivation is not so important for today's talk. So the idea here is, OK, when you do an LP relaxation, always what you try to do is you think about your optimization over a discrete set. So here, these are not nodes. I really mean this is like cycle 1. It's like a feasible solution. This is another cycle, and so on. And I'm trying to optimize some cost. So let's say it's linear. Whole idea of LP relaxation, of course, is just this geometric picture. You take the convex hull of your decision set, and now you optimize over that instead. So this LP relaxation is really just doing nothing but that. So I've separated into two steps, sort of simple things. The first is just purely notational. I'm just going to translate from a cycle to a cycle matrix. So for example, if sigma is the cycle 1, 2, 2, 3, 3, 1, then define P sigma as 1/3, so normalized because there's 3 edges. And I'll put 1s in those entries corresponding to the edges ij. OK, just a simple, nothing deep, just notational thing. The point then is that we can rewrite this average cost in terms of a linear thing. And so then it really fits this picture. Now you just take the convex hull of the decision sets. And the point is there's this thing called the circulation decomposition theorem or flow decomposition theorem. OK, sort of a very standard basic fact in linear programming that if you take cycles, they're convex hull circulations. So if I take a circulation, which is, maybe I'll draw a picture. This will make it clearer. If I have say 0.2. I'll try to draw the arrows the right way this time. 0.2, 0.4, and 0.2. This is a circulation because for every of these 3 vertices, you have the same inflow, inflow minus outflow, so the net flow is 0. And you can decompose this as a combination of 2 cycles, one which is 0.2 on all of them, So 0.2 on all these edges, and one which is, okay, here the numbers matched up to be 0.2, but of course they could be different. All right, so this is sort of the geometric picture of what's going on in comic solving.
This is just to say that the extreme points of this
Absolutely.
equals this as the extreme points.
Absolutely, exactly.
So in what sense this is like, you said it's a relaxation?
Exactly, relaxation, if you will.
Okay, so if you get extreme point, then you solve this.
Exactly. There's no changing the problem. I'm just reformulating an LP so I can make the things more parallel. Perfect. Okay, so at this point, we've sort of fully introduced parallel formulations of transport and min-mean cycle. I could introduce, or people study matrix scaling, matrix balancing in their own right, of course. These are famous problems, in their own. So depending on the community, you might define these first and then take the other ones as sort of approximations. How I'll introduce this is, going from the first row and then saying, what's one possible algorithmic approach to get to the second? Depending on the community, if you start from a different place, you can think about this as a glue in either way. Okay, so, maybe I should say first, this is just a summary of what we've said so far. Optimal transport and min-mean cycle are both linear programming over sort of the objects on the left or the right. If you like graphs, matrices, distributions, there's exactly a dictionary to go between these. We talked about bipartite flows versus circulations. When we take the matrix version, it's exactly what's called the transportation polytope, fixed row and column sums, or free row and column sums but just equal, called the circulation polytope. And if you like probability, you can think about these as joint distributions with fixed marginal, something we call couplings. I asked some friends, no one knew. If you have a better word for this, let me know. I'm just going to call this self-couplings. It's coupling with itself. Okay. All right, so those are those problems. Now we'll talk about how to connect it to matrix scaling and matrix balancing. Okay, so as I said, the way I'll motivate this is through algorithms. I guess my background's optimization. So imagine I want to solve these two problems, optimal transport min-mean cycle computationally, for large graphs, large size n. There's, of course, many, many different ways to do this. I'll describe this, it is an algorithmic approach, but I'll describe this more as just a glue to introduce the other problems. So one natural algorithmic approach is to make the problem more convex. Of course, many convex regularizers you could use. Because these are optimization over distributions, one natural one is entropic regularization. So you add some amount of, negative Shannon entropy, which is just you treat the joint distribution, sort of vectorize and do Pij log Pij. This is strongly convex with respect to the right distribution metric, L1, by Pinsker's inequality. And so as you add more entropy, you make the problem sort of more convex in a sense. Of course, you're regularizing, so it makes it less accurate. There's a certain way you can trade off these things to make sure you're still reasonably approximate and hope to benefit from strong convexity. For the purpose of this talk, I'm not going to really bother too much with the details about eta, but just, these problems can be made approximate. Okay, in any case, let me emphasize this is just one choice of regularizer. You could use many other regularizers to make problems strongly convex. What makes this one special is really that it provides the glue between the first row and the second row of the story. So there's this two lemmas, which are classical and have been reproven many, many times since, over the last 50 years or so. So I think this one is attributed originally to Wilson in 1960. I think this one's also very classical. There's a nice survey about matrix scaling and balancing by Adele about 10 years ago, and so you can read about that more for the history. In any case, if I choose any regularization eta positive, I'll call that entropic OT. So it's exactly just this original minimum over joint distributions with marginals linear cost, but now I just add a bit of entropy. This problem is equivalent to matrix scaling, an auxiliary matrix. This auxiliary matrix is what you get by entry-wise exponentiating your input cost C. Okay, so I should define what matrix scaling is. Perhaps this is somewhat more familiar to the optimal transport crowd. The idea here is you want to find Okay, you form this matrix that just entropy exponentiate. It's given to you. It's sort of not a hard thing if you're willing to write n by n matrices. You're trying to find two diagonal matrices before and after so that when you multiply them all through, you get the right marginals. Okay, I think this problem is familiar to, or perhaps more familiar to the crowd here, so I'll focus more on the second one. I'll say more about this soon. The point of this sort of story is that you have almost this, you have really the analog story also for the second column. If you take min-mean cycle and you do entropic regularization, you get a problem called matrix balancing, which looks very similar to matrix scaling, except for two things. One is I want symmetric marginals, not fixed, something we've talked about. And second, instead of having two free diagonal matrices, we're going to have just one. So it'd be dA d inverse. So as a sort of very, very simple toy example, oh, okay. Okay, actually, let me so let's do an example. So this is essentially the 2x2 example from Osborne's original paper in 1960. So if I take a matrix which has some very small values and some very large values, say 10 to the 8th and 10 to the negative 8, I'll call this my matrix A. Maybe I want to compute eigenvalues of this. Or maybe as another application, I want to solve min-mean cycle, then big and small entries are very reasonable because of exponentials. In any case, this is sort of not very stable for numerical computations. And what you can do is if you can find a matrix D and write its inverse, so that when you multiply out, it actually looks a lot better. And what matrix balancing would tell you to do is take this matrix 10 to the minus 4, 10 to the 4, so the inverse will be the opposite. And if I did my arithmetic right, this will be much nicer looking matrix. This multiplies the first row by 10 to the minus 4. This multiplies the second row, right? So this is really multiplying rows. Each of these multiplies the columns. So 10 to the 4 multiplies the column. 10 to the 4 multiplies the column. OK, so that's maybe a very simple example of matrix balancing. There's one small nuance in this connection that when you scale like this, you're not going to get something which is normalized. So to make this connection precise, you also would just have to renormalize by the total sum. Here you don't need to. It's going to be automatic from the mu and nu. OK, but this is just a detail. The main point so far is that there's really a glue between the first row and the second row by going from LP to entropic. All right.
So, sorry, here you're saying marginals, but do they have to be probabilities? Do they have a sum to one constraint on that?
Very good. So I'm using the word marginals for M because I'm going to really just care about the normalized one at the end, and then it is a bona fide marginal. Yeah. So this has M1 equals M transpose 1 if only if the normalization P1 equals P transpose 1. And that's sort of maybe the right mathematical statement.
But what I'm thinking about is like if you consider the first problem by saying, mu and u are equal and I'm optimizing over this, I'm minimizing also over mu.
That's one way of reforming it as a bi-level thing. Yeah, totally. OK. So maybe at first glance, this feels a bit surprising if you haven't seen these things, but it's actually sort of a very natural thing if you look at the LP and regularized versions of these. These are convex programs, and really all this equivalence is doing is sort of a duality statement. So what I'll go on is that, OK, so you'll have LPs and a dual LP, you'll have a regularized thing and a dual regularized problem. And always P will be the primal variable. Always your dual variables will be these scalings, what I call them X, Y, and D. And this equivalence is just the optimality conditions KKT. So I'll flash just very, very quickly a big table of these formulations. The point is not to parse these. The point is just to see the similarities and this sort of syntactic connections. So this first, OK, this is a bit small. This first table is about optimal transfer matrix scaling, so just the left-hand side. And the only point here is that the first row, you have an LP and its dual, whatever it is. The LP is over P, our couplings we've talked about. The dual is over, we have two vectors, because you have to dualize two constraints. What we talked about, this glue, is that when you go from the LP to optimal transfer to scaling, you just add entropy. That's the only difference here. From convex duality, if you do entropic regularization, the primal, in the dual, it's soft-min smoothing. So replace the min with a soft min, so log some x, whatever, with negatives. And the point here is that this is actually exactly the dual variable. So these vectors x, if you exponentiate them appropriately, then the matrices you want are exactly these diagonals. Okay, so the point is basically, if you solve the primal, you get the entropic OT. If you solve the dual, you get the balancing. These are linked through KKT conditions. And the point of the second table is just that you have exactly the same story when you go from fixed marginals to symmetric marginals. I've highlighted in purple the only difference here. Instead of fixed marginals, you have symmetric. Again, you have LP, dual LP. Because you only have n constraints, you only have n variables. In any case, when you regularize entropy down here, same thing. And the dual, again, min to soft min. And again, you have the left and right being the equivalent. So the left is the entropic MMC solution. The right tells you the optimal matrix balancing. So again, you'll have this transformation about if you exponentiate diagonalize, that's your optimal diagonal matrix. OK. So again, the details aren't so important. I'm just trying to highlight the syntactic connections. All right.
Yeah. For the first one, can you put the first one down?
Mm-hmm.
You see, for the first one, maximum, you see, usually I'm used to the case that you assume that Cij minus xi minus j greater or equals than 0 and take maximum. But here you slightly do it differently.
So
the dual standard dual in linear programming would be you assume that you have a constraint Cij minus xi minus yj greater or equals than 0, and then you take maximum.
absolutely. OK, so these will be equivalent. I've done a small sleight of hand just so that I can make the top to bottom look more similar min to soft min. You're absolutely right. The proper LP dual, sort of in its proper form, would have this in the constraint. You can move it up here in this way. It's equivalent, just so that I can make this a bit more similar.
Okay. But you would have constraints also in the soft dual?
No, this will be unconstrained.
Okay.
Yeah.
This doesn't have another form. Though.
No, exactly. And that's just why I wrote it in this form, just to highlight the parallels. OK, great. So we've talked about problem formulations and the geometry. This perspective also lets us unify the algorithms. So Sinkhorn's algorithm is probably familiar to most folks in optimal transfer community. Osborne will be the analog here. OK, so Sinkhorn's algorithm, again, what's the goal? You want to find diagonal matrices x and y so that when you multiply out, you have the right marginals. As we've said, x controls the rows, y controls the columns. So what Sinkhorn will do is just the simplest possible thing. I'll initialize to identity, so no scaling. And I'll just update always all the rows by updating x, or updating all the columns by updating all the y's. So just alternately update, and there's a simple closed form that just says if I want the first row to be twice as big, multiply x11 by 2. All right, geometrically, this is doing something very nice. So here, if I imagine my coupling matrix, I have two types of constraints, the row sums being right, column sums being right, both linear constraints. What's doing is a certain projection, a KL projection, whatever, but it's a certain projection onto these two things. In the dual, what's going on, and by primal dual, I really mean upstairs in those formulations we just talked about. In the dual, you're optimizing over these matrices, maybe the log versions, And it's doing a very nice algorithm, block coordinate descent. So here I have sort of a toy example, or a toy cartoon, where I have one dimension for x, one dimension for y. I have the contour plots of the dual. What I will do in this first step is I'll fix y, and I'll find the best x. Then I'll fix s, find the best y, and so on. OK, and there's this exact equivalence. All right, so this is probably familiar to most folks here. Let me tell you about Osborne's algorithm, and I'll try to highlight the similarities. So here, as I've said, we have almost the same problem, but we only have one matrix D. And when you multiply out, you want to have symmetric marginals, not fixed. OK, but you could try to play the same game, and that's exactly what Osborne did. So initialize these to identity, no balancing, and then just try to update them in sort of the analogous fashion. So maybe rescale the first row column pair, then the second, then the third. You can't do them all at once because they interact with each other. So that's one important difference, and this will play a very important role what's to come for the analysis. And Sinkhorn, all the rows are separate and all the columns are separate. So it's just A, B, A, B, A, B. Here, you have to really do 1, 2, 3, 4, 5 to n. I mean, you can't parallelize beyond that. OK, in any case, if I want to update the ith row column pair, I can just find dii and update that one thing. A simple closed form just to make the row and column sums equal. And again, in the primal, it does the same thing. Now I have multiple constraints, because I have row 1 equals column 1, row 2 equals column 2, and so on. So if I update the second column, or second pair, then the third pair, then the fourth pair, back to first, I've done a cycle, and that should be the analog of doing a row column in Sinkhorn. One important note that will come later is that what's actually implemented in all algorithms for 60 years is the cyclic order. If you do different orders, it's a variant of Osborne. It's totally fine to analyze, and we will talk about that too. But I just want to emphasize the original thing that's actually used is cyclic one. OK. In the dual, it's doing coordinate descent, and it'd be exactly the same picture. I just can't draw in higher dimensions. So. OK, so that's the analog of these two algorithms. So now I'll move sort of to the second part of the talk, which is about runtime analysis. OK, I guess this is just finishing up the story. We've talked about everything up to here. Now you could ask how fast these algorithms actually run. In practice, these have both been used for a long time. As I said, Osborne is sort of it is the default in MATLAB, R, Julia, Python, et cetera. Sinkhorn is the default in many optimal transport modern solvers for large-scale things. In practice, these typically are documented to converge in roughly n squared time, which would be sort of the best possible, because reading the input matrix is n by n, unless you have more structure. And I guess a key challenge here is just how do you actually show these convergence? From those pictures, it looks like we're converging quickly. We're making progress every time. But when you make progress in one thing, you sort of mess up the other. If I correct the rows, I mess up the columns. And so there's been a lot of beautiful work about different ways of quantifying this progress. For example, perhaps you're familiar with Sinkhorn contracting in a certain Hilbert projective metric. There's also been very nice work about permanent potentials by others and many more. For the purpose of this n squared runtime, these are insufficient. So for example, the contraction incurs extra factors of n and will not be able to give you the best possible dependence in n. So sort of the results I'll highlight here is that for both Sinkhorn and Osborne, we were able to show that these two algorithms in exactly the original form converge in n squared time. I won't focus on the epsilon too much here, but like this is the best possible for dependence on it. OK. So I guess that was the high-level unifying story. What I'll focus on in the last 15 minutes, perfect, is I'm going to zoom in now on matrix balancing, which was, I guess, the title of this talk, and Osborne's algorithm, which I've now introduced. And we'll talk about the runtime analysis, sort of at least some ingredients that go into this, and a bit more history, because matrix balancing is interesting in its own right. And I'll talk about how you can analyze its progress using Hillinger divergence. Yeah, questions before we move on? So it's a convex program. So there's yes, yeah. So the LP, when you add entropy, it's also convex. So you take the dual, it's also convex.
And it does
with a small asterisk, maybe two asterisks. One is that it needs to be irreducible. So if your graph has two sort of separate parts, then you can balance both separately, and there's some dumb reasons that it's not unique. But if it's irreducible, it will be unique. At least dA d inverse. D itself is not unique because I can multiply d by 5. If d is 5, then d inverse is divided by 5 is the same. But the actual quantity you care about, dA d inverse, is unique.
Okay. I have a question about the philosophically, if you take the optimal transport without entropy, even if it's n cube, you have a LP is so efficient that you can store a very, very large problem. So isn't it the motivation to have the entropic version, to have that the result is more robust to noise or these kind of things? Because in terms of computation, you could solve the zero entropy, the epsilon equals 0, and do a basic LP or the Hungarian method. So
Yeah.
what is the really motivation for the entropic version of optimal transport and balancing also?
Great, so maybe two separate answers. One is that for the purpose of this talk, I'm only introducing this as a glue to these problems so that I can focus in on matrix balancing. But your question is a very good one, sort of maybe for a different talk, but I'll give you a quick answer. If I cared about solving optimal transport by itself, why would I do entropy? So you're totally right, there's many different algorithms to solve optimal transport by itself. N-cube types linear algorithm, N-cube time algorithms, very classical, as well as some recent breakthroughs that are n squared in high accuracy, although perhaps not practical yet with Laplacian solvers. The reason for doing entropic versions, I guess we'll see more in actually later talks today. There's a couple of reasons. One is statistical versions. If you care about mu and nu as actually coming from samples, then it can have better statistical properties. One is robustness, like things you're mentioning there. Also, computational pipelines. People often use this not as the end goal, but a means to an end. So they put this as the last layer in a neural network. And the nice thing about entropic things is you can differentiate through it. So you can actually use this as an intermediate block. Computationally, this is nice because it's super simple to implement and very parallelizable, so you can distribute this very well. But of course, there's a whole story here about, depending on what you want from the problem, there could definitely be different algorithms for it. If I want to solve a smaller size problem to high precision, you should never do Sinkhorn. It's just totally the wrong approach.
So maybe I can answer your question. You see, classically, if you take a flow algorithm, it's O n cube log n, and here's this O n squared.
Yeah.
That's a main difference. But the second remark is in the dual formulation, you have a concave functions because you maximize. In the dual formulation, it's maximum of a concave function. But it's okay. You take minuses, you understand the difference. You cannot maximize fast convex function, but you maximize concave function. The dual is concave function.
Yep.
Relaxation.
Whenever you go from min to max dual, it will be convex concave. Yeah. So, okay. I think these are all sort of a family of reasons, and happy to tell you about more, but hopefully this answers your question. Okay, so we have about 10 minutes left, which is perfect. So let me zoom in on matrix balancing. Okay, so I've already said the problem. Let me briefly mention why this is an interesting problem in its own right. So I've introduced it as maybe a means to an end for min-mean cycle, but people have, of course, studied matrix balancing before that, and the original motivation was from Osborne. He wanted to compute eigenvalues of matrices, and you could have matrices like this, which have big and small entries, and he observed that numerically, if you run eigenvalue algorithms or anything, any types of numerical linear algebra, they'd be unstable. But if you just balanced it first, things would work a lot better. So you're proposed to use this as a pre-processing step. And if you look at sort of modern textbooks, they'll say it's recommended to use this whenever. In practice, it takes n-squared operations. This is this is documentation of a practical fact, not a theorem. And so nowadays, it's used quite often. It's also used in different places. So anything else with eigenvalues, it's used, right? Because dA d inverse doesn't change eigenvalues. So if you want to do matrix exponentials, it's also used by default in R and other packages. There's a nice survey by Schneider and Zedios that describes application economics, and used in other places as well. Okay, I should mention an important note is that you can study matrix balancing in any norm. So right now I'm saying scale it, make your first row equals first column. So I'm summing the row, summing the column. It's an L1 type thing. You could, of course, ask this to have any other norm on the ith column and ith row. And the sort of the quick of the story is that all the software packages I've mentioned use L1 or L2. And L2 is really just a historical artifact. L1 is equivalent for a reason I'll mention in a second. Trivial reduction, it's more numerically stable because you don't have to square and square root. It's faster because you don't have to square and square root. So this is the standard. So I'm just going to study L1 in this talk. It is equivalent, though, to all LPs for P finite. For a simple reason, if you do LP of a matrix, that's the same as doing L1 of the 1 over pth power. So if you care to do L2 balancing, you could entry-wise square all your matrices, do L1 balancing, you get the same solutions. So I'm just going to focus on L1. I should mention an important thing is there is something different in the LPs. If you take L infinity, it does have fundamentally different behavior. It's a very interesting problem in its own right. Arguably much more complicated. Existence uniqueness is much more difficult. That was only sort of proved actually in the 90s, 2000s. And I'll emphasize there was this really nice breakthrough by Shulman and Sinclair, who actually revitalized this whole field. They were the first to prove polynomial runtimes for the L infinity version, which does not imply it's just different than the L1 or LP finite versions, which we'll study. But this was a nice breakthrough which really revitalized the field.
Would that make sense to speak of balancing in the non-symmetric case by taking, maybe if you have the A matrix, A transpose balance? Is it used somewhere?
If you take a symmetric matrix, always the rows and columns will be equal. So A transpose will be balanced without doing anything. I don't know if that answers your question.
Okay.
Yeah, so good question. So this is always used for computing eigenvalues of non-symmetric matrices.
Non-symmetric, okay.
Yeah.
So for symmetric matrices, it doesn't give anything.
For symmetric matrices, you would not need to balance, correct. Great. Okay, so yeah, this was all just the same. I'm going to focus just on L1, but I want to make sure that you're aware of the other parts of the world. Okay, so a quick dash into the history behind this. So Osborne first proposed this in 1960. There was a lot of early work on asymptotic things like asymptotic convergence, uniqueness and existence to your question, which comes down to irreducibility. These are asymptotic results. It was not until this recent breakthrough that I mentioned of Shulman and Sinclair that people showed polynomial runtimes, sort of 30 years later, for L infinity. And then folks at UCLA, so Ostrovsky, Rabbani, and Yousefi had a breakthrough to show also polynomial runtimes for LP finite. Okay. So these are breakthroughs. They have polynomial runtimes. One sort of complaint is that these polynomial runtimes are large in the sense that they dominate the runtime of eigencomputation. If this is supposed to be a fast preconditioning step, then you shouldn't spend more time to precondition than computing eigenvalues. And also doesn't match the practice, which I had a screenshot before, n squared. So this started the line of work of trying to refine this to get actual things that match practice. The original version of Osborne was difficult because of the cyclic order of coordinates. You do first the first row column, then the second, then the third. It turns out for different variants, it's easier to analyze. So the same paper of Ostrovsky, Rabbani, and Yousefi showed an n squared runtime for if I choose the best coordinate to update, or if I choose a certain weighted random version. There's some extra overhead here, but this is sort of a bona fide n squared runtime. With Pablo, we showed how to exploit sparsity to go from n squared to O of m, sort of number of non-zeros, and also use a simpler algorithm, sort of just uniform random, choose every time. Okay, but despite that, that's not the algorithm people actually use. Everyone's always been using the cyclic order, and it is better in practice for a number of reasons. Seems to require fewer iterations. An important, okay, I guess really engineering thing, but very important, is you're accessing adjacent rows and columns when you go in cyclic order. So it's cache friendly, and this actually makes a difference in practice. There's no extra overhead for updates. You don't have to find the greedy, find the best update to. This automatically exploits sparsity. You're not going to accidentally look at really dense rows every time. And also, it's very stable to using low precision. So you can see this in plots. I mean, I guess I don't really need to show plots, just the fact it's It's the default is already evidence, but you can plot these different things, and you can always see cyclic is faster, whether it's on sort of random inputs that you change or sort of hard instances. And so the question is really, how can you analyze this original version with cyclic updates? Okay, so this is the main result I wanted to get to. With Xufeng Tsai and Jelena Diakonikolas, we very recently posted a paper which has O of m runtime. So, okay, m is n squared if you think about a dense matrix. This exploits sparsity. Some details I'll explain in a second. The main point is this is near linear in M, and this is the original algorithm. This is what people actually use. Okay, there's some details. So this log kappa is somehow the sum over the min. You can think about this as like max over min. It's in the log factor, so it's not so bad. And this is needed for all other analyses and all different variants. This epsilon is the TV between marginals, sort of like you have in optimal transport analyses. If you like, you can think about this just as 1 over epsilon squared. That's good enough for this talk. I just point this extra thing that there's a benefit you can automatically accelerate. So in optimization, we say 1 over epsilon squared to 1 over epsilon automatically accelerates if your diameter is small. This diameter quantifies how balanceable you are. Balanceable, we said, is equivalent to irreducibility, which means your diameter is finite. If your diameter is not just finite but small, this accelerates. So for example, if you have a dense matrix, fully, everything, diameter is just 1. It's fully connected. So this is just 1 over epsilon. But okay, this is details. The main point is just m.
What is A mean?
Oh, sorry, the input matrix is A.
Okay. And A mean in the numerical.
Oh, sorry, the minimum non-zero. Thank you. I should have said that. So then extends to sparse things. Okay, so a couple quick remarks. Okay, this improves mn squared to m, matches practice, no longer dominates eigencomputation. We call this near linear time because the log kappa has implicitly a single log n. That's the only extra or possibly, extra factor beyond the linear runtime. And I'll mention this also improves or matches all other variants and all parameters. So, this is, yeah. Okay. There's also a very beautiful line of work starting from work of Kacyan in the 90s, the ellipsoid. He used ellipsoid stuff to do an alternative method for matrix balancing by directly solving the convex optimization problem. It's been recent work, very nice work by Maudry's group at MIT and Wigderson's group at IIS, who develop alternative algorithms. They're not currently practical. They use Laplacian solvers. So I'll mention, I guess, the main differences is one, this is actually implemented, and second is even if you compare apples to apples, actually in regimes of interest, this simple algorithm actually has faster runtimes. Okay, some other minor remarks. Let's see. Let me give you and I wrote briefly, because I don't intend to go into details, but just a quick sense, very quick sense of what are some of the ingredients that go into this. And this will get us to this final row. Okay. All right, so as I said, the challenge here is how do you measure progress? When you update one row column pair, you mess up the rest. So the sort of starting point is to use this convex optimization objective, which has played the predominant role everywhere in connecting everything. We'll use this as actually just the potential to measure progress. Okay, so I've rewritten things in sort of a nice way with the log sum x. I'm taking eta to be 1 just to simplify things. In any case, this is the dual potential. I'll call this phi. And x is the dual variable. If you put this in diagonal form and exponentiate, this is our d we're trying to find. Okay. There's some nice connections. If you take the derivative, you can check this is exactly the L1 imbalance. So really, by trying to minimize this function, we're trying to balance. If the gradient is 0, then you've balanced. So in other words, if you balance, you have a minimizer. If you epsilon balance, then you have an epsilon minimizer. Sorry, epsilon stationary. So these are really equivalent. And as we said before, Osborne is equivalent to coordinate set. Okay, so this is sort of the pretext, sort of the background about why this is a reasonable, mapping. What we'll use today for this potential is just two very simple facts. And I won't show the proofs, but they're just sort of 2 lines. You can look them up in our paper. So First is that the potential is not too far from optimal. So if I have phi of 0, this is my potential when I have no balancing. This is phi star. We're saying that this is not too large. And the second is that every time we update a coordinate, we get large progress. So we improve by the current imbalance as measured in this particular way. And this is just from plugging in the definition in Osborne. It's really just a simple calculation. It's just effectively inequality with, OK, and the analysis is now just basically one step. So this is from updating a coordinate I. If you take a random coordinate, then you take an expectation over which coordinate. This you'll recognize for the statisticians in the room, or probabilists in the room, this is just the Hellinger divergence. That's the entry of this final term here. There's a basic inequality that Hellinger upper bounds TV, up to some constant 2 or whatever. And we said that this is exactly what you want to be small. So if you're not epsilon balanced, then your progress is at least epsilon squared over n. Which is to say, in this picture, you've made at least this much progress. If you make big progress, and there wasn't much progress you made in the beginning, you can't go many steps. So the total number of steps is at most this gap divided the per iteration progress. OK, and this gives you a certain bound, has some details. The main thing is an n here. That's the number of iterations you need. Each iteration requires summing up a row and column. That's roughly n arithmetic operations. If you're sparse and you're doing a random thing, then the average sparsity is not n. It can be improved a little bit to m over n. Multiply the number of iterations by iteration complexity, and you get the final bound. So n times m over n is m. OK, so this is the idea for random. I'll mention just very quickly that one upshot of this, one thing I'm excited about, is that this mirrors exactly our analysis of Sinkhorn for optimal transport from a while back, where we did exactly the same argument, or as similar as possible, with the KLA divergence for Sinkhorn. So what I've just shown you is that actually this mirrors, not just problem formulation and algorithm, but also the analysis. Let me just say one last thing, and then I'll take questions. So this was for the random version. The recent result I advertised is that you can also do this for the original cyclic thing. Okay, I wrote very briefly because I don't want to go into details. I'm just going to say the main challenge is you have cyclic updates. Cyclic coordinate descent is, in general, very difficult to understand for convex optimization if you want to get sharp bounds. Traditionally, it's been a sort of a challenging question to get optimal dimensionality factors. And that's exactly the game we're trying to play here. The main idea is that there's a way to sort of an analog of the first lemma, progress lemma, and a second thing. And the second thing is key because what happens, so just the main point, is that these are about the imbalance exactly when you update them, which is always the challenge in cyclic methods. Because if you update them at the, maybe there's a good coordinate to update right now, and if you do a random or greedy, you can choose it. But if you do cyclic, you don't have a choice. And by the time you get there later in the cycle, it could no longer be good. So this lets you charge exactly the imbalance when you update them. And there's sort of a, at least conceptually simple idea. If the balance is small, if you get a small update, then this imbalance lemma says that you're actually good at the end of the cycle. You can terminate. If these are big, then you get big progress. And you can argue the same thing. You can't have big progress too many times. So eventually you have to be in the first case, and you're done. Okay, of course, the casework is much more sophisticated. That's the main idea. So I'll just end with this. The main takeaway today was a unifying perspective on problem formulations, algorithms, and analyses. And I just focused on one particular result, which is a near linear time for Osborne's algorithm. All right, sorry for going a couple minutes over, and thanks for listening.